I ended the last video by promising I'd be right back, and it's taken me, 3 or 4 days to get here, so I apologize for that. I've been struggling with trying to decide how best to do this. I love this lesson. This bit of math is a lot of fun, but it works best on a whiteboard. And so to try and do this here, drawing pictures and writing numbers with my mouse is going to be clumsy, and I apologize for that in advance. But let's try and get through this, see how it goes. Okay, so I apologize in advance, but let's get through this. So here's the slide I left off with in the previous video. This is not an exhaustive list by any means, but it's an example of the kinds of notations that we're going to be looking at. Okay, it says there phase values versus line values. Well, what values are we talking about? Well, you can see that we're talking about E, which is voltage, and I, which is current. Those are the values that we're going to be calculating. Okay, and then there's this thing called phase versus line, and that's what the subscripts are here on these notations. So E subscript L means what is the voltage in the line. Okay, and then the next one is E subscript and this and I forget the name of this particular symbol off the top of my head, but it represents the phase. Okay, so we're going to be calculating voltages on the line, and we're going to be calculating voltages on the phase. And in just a moment, I'm going to talk about what that means. Then there's going to be the current in the line and the current in the phase. And then I'm going to add one more part to the notation. The final bullet there shows E subscript PL. So that is the voltage on the primary line. So we've talked about transformers having a primary coil and a secondary coil, okay? And we want to talk about what are the voltages on that primary coil and on that secondary coil, or the line. Okay, let's get started on this. Here's where things are going to get interesting because I have to try and do some drawings for you. Okay, but let's start. Whew. See, this is, I apologize in advance, guys. That's actually supposed to be a coil. Okay, so that is, let's call that the secondary winding of a transformer. Okay, so this is referred to as the phase. When we're calculating values, when we're calculating currents and voltages, we will call the coil, the transformer coil, a phase. And so the question is, how much current is flowing through that coil? And that is I phase. Okay, how much current is flowing through the coil? Okay, and then we are going to connect wires to that coil. Okay, so we're going to make a connection right here. Whew, that's supposed to be a dot. And there's a wire, call that line 1. And then we're going to make a connection here. And we're going to call that line 2. Okay, so we've identified I phase as the amount of current flowing through that coil. Okay, I line then is going to be the amount of current flowing through that line. Okay, likewise, E line, well, I probably should have started with the conversation about E phase, but that's okay. E line asks the question, what is the potential difference between line 1, and line 2? Okay, the potential difference between those is E line. Okay, or E phase. Okay, what is the potential difference across that coil of wire? Okay, that is E phase. So what is the voltage there? What is the potential difference, okay, across the coil and across the line? Now, recognize that I haven't drawn a 3-phase connection. I've simply drawn a single coil with line 1 and line 2 connected to either side of it. So at this point, you're going to say, well, Dave, those are the same. Okay, the amount of current flowing through that coil of wire, I phase, is going to be the same as the amount of current flowing through that wire, line 1. Okay, and you're absolutely right, because while I drew a dot here, it's not a node because there's no place else for the current to go. Okay, but understand that when I introduce the other 2 phases, the other 2 coils of wire in our 3-phase transformer, there's going to be a connection here. This dot is going to be a node, and that introduces the possibility for voltages and currents to change, which is absolutely what's going to happen. Okay, so that gives you an idea of what our notations are. Okay, E line, I line, E phase, I phase. Those are the variables that we're going to be calculating for. Okay, so let's go back and talk about a delta connection. And we said a delta connection is like parallel. Okay, and what is it about a parallel circuit that we base our calculations on? The thing that we kind of hang our hat on to start our calculations is that in a parallel circuit, voltages remain constant. Okay, so if we go back to our original lessons on using Ohm's law, we know that every branch of a parallel circuit sees the same voltage drop. Okay, so voltage remains constant. So what I want to attempt to do here is I'm going to draw a delta connection. So here's our first coil of wire. Here's our second coil of wire. And here's our third coil of wire. So we've connected them together. Okay, if those were vectors, they were placed tip to tail, right? I've taken that triangle and I've spun it on its side, but the reason I choose to do that is now we're going to add our wires to this. So from this point up top, we're going to come out here and we're going to say that this is line 1. From this point here, we can come out, call this line 2. And from this point, we can come out and we'll call this line 3. Okay, so there's our delta connection, and we can see our 3 phases, okay, our 3 coils of wire in our transformer, okay, and we can see our 3 lines. All right, so voltage remains constant. What that means is, and let me draw the same sort of thing I did on the previous slide. If I ask you the question, what is the potential difference across that coil? What is the voltage rise from that power source? And I'm going to say it's 120 volts. Okay, and now I ask the question, what is the line voltage? Okay, so I'm looking at line 1 to line 3. All right, and the potential difference there will also be that same 120 volts. Okay, same is true all the way through. So if I ask you what is the voltage rise there in that coil of wire, it's 120 volts. And that lines up with the potential difference between line 1 and line 2, 120 volts. So voltage remains constant. In a delta connection, it doesn't matter where you look, you get the same number. Okay? Voltage, delta system, constant. Here's where things get different, and this is why we have to say it's like a parallel circuit. It is definitely not a parallel circuit, because now let's talk about what happens in current. Okay? And the bullet there says the current changes by a factor of 3. So this is what I indicated in the slides before. If everything stays the same, it stays the same. But if things happen to change, they change by how much? Well, they change by √3. So here's the conversation. First of all, we can ask the question, what is the current flowing through that coil? Okay, and we can put a number on that, whatever it might happen to be. But the next question is, that's our phase current. Next question is, what's our line current? So how much current is flowing through that wire right there, line 1? Okay, here's where it's time to recognize that we have a node right there. Okay, so the current's not going to be the same. Okay, the amount of current flowing through that coil is not going to be the same as the amount of current flowing through that wire, because there is a node there and there is another voltage rise involved. So let's put an arrow there in this direction. And now we say how much current is flowing through line 1. Well, here's where we'll apply Kirchhoff's current law, but in spirit only. We cannot apply any numbers. We'll talk about that in a moment. But in spirit, we can recognize that the current flowing through this first coil and the current flowing through the second coil are going to add together in this node. Wow, that's getting messy now. and give us the amount of current flowing in this line. So the conclusion we can get to from that bit of logic is that the amount of current out on the line is going to be greater than the amount of current that we measured inside any given phase. Okay, the current flowing through a coil. Okay, so the line current is greater than the phase current. All right, but we can't simply add the two together. Why not? Because they're out of phase by 120 degrees. Okay, and so because of that, we can apply the logic that the line current is greater, but it's not simply double. Okay, it's greater by a factor of √3. And that's what we see in this equation. The current in the line is equal to the current in the phase multiplied by √3. Now what is √3? √3 is 1.73 roughly. So that means we're going to take the current in the phase, we're going to multiply it by 1.73. So we're going to get a number that's bigger, but it's not times 2, it's not doubled. Okay, it's something less than that. Okay, now I don't want to hurt your heads here and I don't want to overthink it, but the reason that is because these two arrows that I drew here through these two coils, can you see where I'm drawing now? These two arrows, okay, are not entirely accurate. Those currents are not flowing into that node all the time at the same time. Okay, sometimes one of those currents might actually be flowing in the other direction. Because if I got really messy and drew the sine waves again, and we show the sine waves separated by 120 degrees, we can see that sometimes, okay, phase A is positive and phase B is negative. Okay, if we're looking at a particular point in the sine waves as they overlap. So that's the reason that we can't just multiply it by 2, we multiply it by something less than 2, and it just happens to be 1.73, which is √3. Okay, so that's our delta connection. It's like parallel, so the voltage in the phase and the voltage out on the line are the very same, but the current in the phase is √3 less than the current we measure out on the line. Okay, that's delta. Let's try Y. So a Y connection we can say is like series. Okay, so what do we know is constant in a series circuit? It's the current. So let me draw my Y connection. So here's a coil. And then we have a coil here. And then we have a coil here. And again, I haven't drawn the Y like a Y. I've put it on its side so that we can come off of this point. Oh dear. Sorry guys. Let me erase that. I can do better than that, I promise. Let's get rid of that. Try again. Here we go. Oh, that's more like it. Line 1. And then I'm going to draw the connection, put a dot there to represent the change from the line, from the phase out to the line, line 2, and line 3. So if we look at this dot that I drew here, it makes perfect sense that the current we measure in the phase, the amount of current flowing through this coil, and the amount of current we measure out here on the line must be the same, because they are the same, right? That's a connection point, but it's not a node. There's nowhere else for the current to go. So it must be the same. Okay, now it's the voltage that changes. Okay, because we can still keep the like series conversation intact, because if I want to know the potential difference from line 1 to line 2, how many voltage rises must I go through? So I'm going to start here in line 1, I'm going to work my way back, and there is a voltage rise, and then there is this nasty node here, okay, but here's a second voltage rise. Okay, so on our way from line 1 to line 2, to ask what is the potential difference, we have to go through 2 voltage rises on that path. And so it makes sense that the voltage out on the line will be greater than the voltage within any one of those phases. But once again, they're out of phase by 120 degrees, so we can't just add them up so that the line voltage would be double the phase voltage. Again, we're increasing the value by √3. So here we are again. What is the voltage out on the line? Well, it equals to whatever the voltage is in each one of the phases increased by that factor of √3. Okay, and that's just about it, guys. That pretty much wraps it up in terms of the math. Okay, let's see what my next slide looks like. So here we go. This is what your assignment is going to look like for this week. Okay, and I'm going to push back the deadline because we are so late getting to the actual lesson. But this is what you need to work your way through. Okay, so what we have here is a three-phase transformer. Okay, and so we are going to have to know what the values are out here on the primary line, and then the values here in the primary phase, and then based on the turns ratio of the transformer. Now look at the turns ratio of the transformer. It is √3 to 1. Okay, and that's not terribly uncommon actually. These are really normal transformers. When we're talking about three-phase transformers, because that √3 is such a valuable number, you'll very often find transformers that have exactly that as their turns ratio. Okay, so with that information then we can figure out our secondary phase values, which then come out here to our secondary line values, and finally this is our three-phase load. Okay, so in here, if I wasn't quite so lazy, the drawing would have shown you the coils. Okay, out here, this is a resistor. There's one there, and one there. So this could be quite simply a three-phase load, or it could just be three plain old resistors, single-phase loads, connected together into a three-phase connection. In this case, Y. Okay, so notice, here's the first thing that you have to pay attention to. Notice that the primary of the transformer is connected in a delta connection. The secondary of the transformer is connected in a Y connection. And our three-phase load is also connected in a Y connection. So those are the kinds of details you need to look at. Okay? The fact that the primary and the secondary are connected in different connections doesn't matter in the sense of it doesn't change the operation of the transformer. Okay, the relationship from the primary coils to the secondary coils follows our turns ratio, our √3 to 1. What changes is the numbers as we transition from the line into the phase of the primary and from the secondary phase out onto the secondary lines. So it's the transition from phase to line or line to phase that we have to factor in the way the connections have been made. Okay, so let's work through this one together. So here's the information we've been given. We are told that the primary line voltage is 208 volts, and we are told the size of the resistor is 60 ohms. So each of those three resistors are 60 ohm resistors. Okay, so we start with the 208 volts on the primary line. Okay, so the primary of the transformer is connected in delta. What happens to voltage in a delta connection? So here's the thought process. Ask yourself some questions. What happens to voltage in a delta connection? Well, we said that delta is like parallel. And in a parallel connection, what can we say about voltage? Remains the same. And so therefore, the primary phase voltage, my pointer has gone away on me, is the same value, 208 volts. Okay? So from the primary line into the primary phase, the voltage remains the very same. Now let's go through the transformer. So with a turns ratio of √3 to 1, the voltage is going to go down by that √3 value. Now, sometimes there's some confusion here, so I want to highlight the fact that we're going to see some familiar numbers. Okay, that 208, which is the primary phase voltage, is going to go down to 120 on the secondary phase voltage. All right, which looks like it's got something to do with the three phases. the fact that it's a three-phase system, the fact that we have to calculate based on root 3. But that's not what's happening right here. Understand that this is entirely a result of the turns ratio of the transformer. The secondary phase voltage is 120 because of the turns ratio of the transformer. Okay? So now we have 120 volts in the secondary phase. Let's find out what the secondary line voltage is. Well, the secondary is connected in Y. So what happens to voltage in a Y connection? Does it change or stay the same? Well, a Y connection is like series, which means current is constant, but voltage is going to change. So it's going to change by root 3. Is it going to go up or is it going to go down? Well, remember, this 120 secondary phase voltage represents the phase right there. That is the potential difference across that coil, across that part of the three-phase transformer. Okay, and so now that is connected kind of in series with that, which means we have two voltage rises, which means the potential difference out here is a root 3 higher. So 208, root 3 higher. Okay, so that is our secondary line voltage, 208 volts. Okay, the potential difference between any one of those three lines and any other of those three lines. And finally, we have to know the voltage at the load. Now these are phase values. Okay, most definitely these are not line values, these are phase values. So once again, when we're asking the voltage at the load, the question is, what is the potential difference across one of those resistors? Okay, connected in Y, okay, what happens when we go from the line into the phase in a Y connection? Well, Y is like series, which means current stays the same, so voltage changes, okay, by root 3, up or down. Well, when we came from the secondary phase out onto the line, we went up by a factor of root 3. So when we go from the secondary line into the phase, which is the load, it's going to go back down again. And so the potential difference across any one of those resistors is 120 volts. Okay? Now I have my calculator handy, because here is where, so notice what we've done. We figured out all the voltages. We knew where the voltages started. We could work the voltages across. Now we get to the load. Now we can find out our current. This is right back to Ohm's law, right? So we have 120 volts dropped across a 60 ohm resistor. I don't need my calculator for that, do I? What is the current at the load? Okay, 2 amps. Oh dear. I hope I didn't just mess things up. 2 amps. Good, there we go. Right, 120 volts divided by 60 ohms gives us 2 amps as the load. So here's what I want to point out. This is very important, that when we're talking about current, don't lose sight of the fact that what defines current is the size of the load, right? Of course, how much voltage is pushing current through the load, but also the size of the load. So we have to get over here to the load to calculate the current, and now we can work our way backwards. So if we have 2 amps flowing through each one of those resistors, how much current is flowing through the secondary line? Well, how have we connected our load? We've connected it in Y. And Y is like series. What's constant in the series circuit? Current. How much current is on the secondary line? So for example, if there's 2 amps flowing up through that resistor right there, then there must be the same 2 amps flowing out on that line right there. This looks like a node, but it's actually only a connection. There's nowhere else for the current to flow. It must be flowing on line 1. So I can put 2 amps right there. Okay? Now we get back to the secondary phase. Again, it's a Y connection, which means it's like series, which means current is constant. We can see the same thing here, that if that 2 amps is flowing here, it must turn and come down through this first coil of wire, that's secondary. Okay, and so we still have 2 amps right there in our secondary phase. Now we've got to go backwards through our transformer. Okay, so let's look at the voltages to figure out what happens. The voltages, as we go back through the transformer backwards from the secondary to the primary, we see that the voltage increased by the turns ratio, which happens to be √3. Secondary voltage is 120. Back to the primary, it went up to 208, which means when we go backwards through the transformer with those 2 amps that we've got for current, if the voltage went up, the current's going to go down. So we're going to have 2 amps divided by √3. √3 equals 1.15 amps. 1.15 amps, right? Everybody see what I just did there? So I just followed what the voltage does, and I know that the current has to do the exact opposite, right? And so what is our primary line voltage then? We have 1.15 amps flowing through each of those primary coils. The primary is connected in delta, so what happens to current in a delta connection? Well, delta is like parallel, which means voltage stays the same, which means current's going to change. So if we apply Kirchhoff's current law, its logic, its idea, we have 1.15 amps entering that node there. We have 1.5 amps entering that node there. We must have more current exiting the node out there in the line. More? By how much? √3. So what is √3 greater than 1.15 amps? The answer is 2 amps. Okay, there we have it. Voltages and currents complete. We're almost done, but things are going to get tricky here for a moment. Okay, let's go. We have to calculate power, okay? And it's asking us for single phase power, and it's asking us for 3-phase power. So remember, all of our numbers so far are single phase. These values are true for each of the 3 phases, okay? Or each of the 3 lines. All right, for power, we want to know how much power is on a single phase and how much power total in the whole 3-phase system. All right, well, how do we calculate power? Power is voltage times current, right? So let's do that. Right here in the primary line, we know, we were told right from the beginning, 208 volts in the primary line, and we have 2 amps we found on the primary line. So volts times amps, 208 times 2 is 416 watts. Now at this point, I encourage everybody to please not stop the video and think you've learned everything there is to learn. Okay, please bear with me. Because, let's try this again. On the within the phase, the primary phase, we have 208 volts times 1.15 amps. Whoops, sorry, let me try that again. 208 times 1.15 amps is 239.2. 239.2, but I don't have room for that, so there it is. Okay, so now how do you feel about that? When we went from the primary line into the primary phase, we lost a whole bunch of power. That makes sense to anybody? Okay, remember we said that while transformers are not 100% efficient, okay, they're 92 to 98, okay, there's some losses, but we're pretty much going to ignore that and we're just going to say, hey, transformers are 100% efficient, we're just going to go with that. Which means the power, whatever we calculate for our single phase power, whatever we calculate for our 3-phase power, should be the same all the way across the sheet. These two numbers are not the same, so we have a problem. Okay? Here's the solution that I want you to fall into. When you're looking at this dilemma and you say something's not right and I'm not sure what it is, here's how you figure it out. Where is that work actually being done in this circuit? Okay, and the answer is at the load, right? So our transformer here, our primary and our secondary, are providing the power, but the work is actually being done by those resistors at the load. So let's calculate our power there. Okay, so what is our power at the resistors? Well, it's 120 volts pushing 2 amps. 120 times 2 equals, oh, I've done it again. equals 240. 240. So that's the right answer. So when we come back here, we look at the 239. That was 239.2. So some rounding error there, but that is the right answer, 240. This number here of 416 is the wrong number. That's the wrong answer. Because we calculated that using line values. Okay, you cannot multiply the line voltage times the line current to get a power value. It gives you the wrong answer. Okay, you must use phase values. Okay, now how do we find the three-phase values? Well, it's simply 3 times. So if we found 240 to be, that's 240 watts. If we found 240 to be the single-phase power, three-phase power is simply 3 times that. So that's 2, 4, 6, 720. 720 watts to be our three-phase power. Okay, now one last trick and I'm done, is this number right here. Oh, why do I keep doing that? This number right here, 416, which we calculated using our line values, we can actually still use. Okay, and the answer is root 3. The beauty of three-phase is that the answer is always root 3. Okay, this 416 has to go from this location. 416 doesn't belong in there. But let me just write it over here for a second. 416. We can use that number because 416 divided by root 3 just happens to be 240. Or 416 multiplied by root 3 just happens to be 720. So we can use our line voltage and line current to calculate power, but we must add one additional step. Okay, the voltage times the current equals a number which is either root 3 bigger than the single phase power or root 3 smaller than the three-phase power. Okay, and that gives us all of our answers. So I'm not going to fill in the rest of those blanks because they're all the same numbers. When you get to the exercise sheet, I'm only going to ask for your power values once because it's the same across the board. Okay, I would encourage you to double check it, check your work, because it'll tell you if you've made a mistake or not. But that is how that falls into place. Okay, so the exercise sheet I have for you is just this with some variations in the connections. Okay, a Y primary, delta secondary, delta connected load, and combinations thereof. Okay, so it mix and matches a little bit. It's fun for you to see how the numbers change. Okay, we always start with the same voltage. It's always 208 volts as our primary line voltage, and they are always 60 ohm resistors. Actually, I may have changed those numbers, but it's consistent throughout the entire exercise sheet. Gives you a chance to see how the numbers move and everything changes just by changing the way we make our connections. Same power supply, same size load, but things change drastically when we just make different connections. Okay, so that is the end of the three-phase lesson. I'll get the exercise sheets out there for you right away, and they won't be due until, I would say, early next week. Give you a chance this weekend and even into next week to work on that and get that to us. Okay, thanks guys. We will be back in touch soon enough.